Welcome to our deep dive into the world of bearings. Whether you're an engineering enthusiast or just curious, join us as we unravel the basics, explore different types, and discover how these engineering marvels keep our world turning. To start, let's journey back in time. Picture the heart of a wheel hub, the conventional journal bearing. In the early days of engineering applications, conventional bearings were commonly used to support rotating machinery. They were simple, functional, and a testament to early engineering technology. However, as the demand for higher speeds and heavier loads increased, the limitations of these conventional bearings began to surface. These bearings relied on sliding surfaces, which led to significant friction and heat generation, ultimately restricting their efficiency and causing wear and failure at higher operating speeds and loads. To address these challenges, the rolling bearing was invented as a groundbreaking solution. The rolling bearing was designed to reduce friction and enhance load carrying capacity by introducing rolling elements between the inner and outer rings. Imagine a simple mechanical setup consisting of two concentric rings, an outer ring and an inner ring. In the wheel hub example, the inner ring is mounted in a way that allows it to rotate around its center, while the outer ring remains fixed in place and does not rotate. Now, let's introduce a roller into the picture. This roller is a cylindrical object with a circular cross-section. It is snugly fit between the inner and outer ring. As the inner ring begins to rotate clockwise, it imparts a tangential velocity to the roller. This means that the surface of the roller in contact with the inner ring receives a certain speed in the opposite direction. This is due to the friction between the roller and the inner ring surface. Since the outer ring is stationary, one side of the roller remains in contact with it, both preventing any rotational motion and initiating the roller's roll along the interface between the inner and outer rings. This innovative design allowed for smoother motion and significantly lower friction, making it ideal for high-speed and heavy-duty applications. The credit for the invention of the rolling bearing goes to Philip Vaughan, a Welsh inventor who patented the first design in 1794. Since then, rolling bearings have revolutionized various industries, becoming an essential component in modern engineering machinery and equipment. To lay the foundation for our journey into the world of bearings, we first need to familiarize ourselves with their classifications, basic definitions, and key nomenclatures. Let's begin by exploring the bearing classifications. Rolling bearings are broadly divided into two primary classifications: ball bearings and roller bearings. First, let's overview the ball bearing classification. We have the radial ball bearings, meticulously designed to support loads perpendicular to the shaft's axis. They utilize balls as the rolling elements, which are confined in deep raceways, ensuring smooth rotation. Then, we transition to thrust ball bearings that are optimized for axial or loads parallel to the bearing's axis, making them essential for applications with predominantly vertical forces. Now, as we explore the classification of roller bearings, we come across radial roller bearings, which, instead of balls, utilize rollers to carry heavy radial loads effectively. Their counterpart, the thrust roller bearings, are similarly structured but focus on managing axial loads with their roller configuration. Transitioning to more specialized designs, we have a category known as special application bearings. These are tailored for unique or niche applications addressing specific industry challenges. Lastly, we touch upon the domain of linear motion bearings, designed to provide free motion in linear directions, often found in various machinery and automation systems. Let's dive into examples for each classification and give a brief overview of their advantages. Within the radial ball bearing category, there's an array of types tailored to meet a range of operational requirements. The deep groove ball bearing is perhaps the most widely recognized. The angular contact bearing is tailored for applications where axial loads come into play. For specific tasks requiring precision and high load capacities, duplex angular contact bearings are employed. The 4-point contact ball bearing uniquely touches the raceway at 4 points. The double row angular contact bearing, as the name suggests, has 2 rows of balls, offering greater radial and axial load capacity. Lastly, the self-aligning ball bearing is cleverly designed to correct misalignments. Moving to the thrust bearing category, we encounter a selection specifically engineered for distinct applications. Among these, The single-direction thrust ball bearings are specifically designed to handle axial loads in one direction. Meanwhile, the high-speed duplex angular contact bearings offer simultaneous support for both radial and axial load. Transitioning to the roller bearing classification, we find a rich variety of types designed to cater to diverse operational needs. The cylindrical roller bearing is known for its high radial load capacity. The double-row cylindrical roller further enhances this capacity, offering more stability. Needle roller bearings with their slender and long rollers are great for tight spaces. Tapered roller bearings with their unique design can effectively manage both radial and axial loads. The double-tapered roller bearing takes this a notch higher with its capacity to support heavy combined loads. The spherical roller bearing with its barrel-shaped rollers is distinctively designed to manage heavy radial loads and is also tolerant of misalignment. Switching our focus to thrust roller bearings, the thrust cylindrical roller is a standout for handling high axial loads in one direction. Thrust needle roller bearings, with their compactness, offer high load capacity in confined spaces. Thrust tapered roller bearings support large axial loads and are resilient against shock loads. Lastly, in the roller bearings list, we have the thrust spherical roller bearings that are designed to manage axial loads in one direction and are particularly capable of accommodating misalignment. Shifting gears to focus on special and linear motion bearings. Please note, in one of our upcoming YouTube videos, we'll offer an in-depth exploration of these special types of bearings. For a quick glimpse, we have the 4-row cylindrical and tapered roller bearings that cater to high-load applications. The ultra-thin section type ball bearings are tailored for space-constrained cases, while the SL-type cylindrical roller bearings bring enhanced performance. The Ultage series showcases advancements across various bearing types, from sealed spherical roller bearings to those made for high-speed servo motors and precision tools. Not to forget the bearings specifically made for unique environments and the clutch torque limiters designed for precise torque management. Lastly, the linear ball and roller bearings pave the way for smooth linear motion in machinery. Ball bearings and roller bearings differ fundamentally in their points of contact with the raceway, their inherent characteristics, and their load capacity. While ball bearings have point contact, roller bearings utilize line contact. Here we will explore their differences, beginning with their interaction with the raceway. When a load is applied to ball bearings, the contact surface takes on an oval shape. In contrast, roller bearings typically adopt a rectangular contact shape under similar load conditions. Ball bearings, due to their point contact design, which minimizes rolling resistance, are particularly suited for applications with low torque and high speeds, and they exhibit excellent acoustic properties. On the other hand, roller bearings, because of their linear contact configuration, experience higher rotational torque compared to ball bearings. However, this design element provides enhanced rigidity to the system. Ball bearings have a lower load capacity, but radial bearings can sustain loads in both the radial and axial directions. Conversely, rolling bearings have a superior load capacity. Cylindrical roller bearings with a lip can accommodate minor axial loads, and when tapered roller bearings are paired, they can support axial loads in both directions. In this section of the video, we're breaking down the types of loads bearings can experience. First, we have the radial load. It's defined as an external force or load acting perpendicular to the bearing's axis of rotation. Secondly, there's the axial load, an external force or load operating parallel to the bearing's axis of rotation. Following that is the combined load. Bearings might, on occasion, face both radial and axial forces simultaneously, giving rise to a combined load with elements from both directions. Lastly, we address the moment load. This specific load produces a bending moment around the bearing's axis. It's typically seen when the bearing deals with an off-center or misaligned load. Understanding these distinctions is crucial, especially as we move on to rate each bearing's capability based on these loads in the upcoming sections of the video. Here we will explore the definition of contact angle for bearings. The contact angle in bearings refers to the angle formed between the applied load direction to the bearing and the line of contact between the rolling elements, be they balls or rollers, and the raceway, often referred to as the inner and outer rings. This angle is pivotal in determining the load-carrying capacity of the bearing, specifically in relation to radial and axial loads. In ball bearings, the contact angle is typically small, resulting in point contact between the balls and the raceways. This design offers low friction and high-speed capabilities, making ball bearings suitable for applications requiring high precision and speed, such as in electric motor. On the other hand, roller bearings have a larger contact angle, allowing for line contact between the rollers and the raceways. This design handles heavier loads and provides improved stability under axial and radial forces. Consequently, roller bearings find use in applications where higher load capacity and shock resistance are crucial, such as automotive components. Bearings with a contact angle of 15 degrees or less have a much greater radial load capacity and are classified as radial bearings, whereas bearings that have a contact angle over 45 degrees have a greater axial load capacity and are classified as thrust bearings. There are also bearings classified as complex bearings, which combine the loading characteristics of both radial and thrust bearings. These bearings usually have a contact angle between 15 degrees and 45 degrees. It's essential to select a bearing with the appropriate contact angle based on the primary type of load it will experience in its application. Allowable misalignment is a critical factor to consider when selecting and using bearings in various applications. Self-aligning ball bearings are engineered to accommodate misalignment between the shaft and the housing due to their design that incorporates a spherical outer ring raceway. This design allows them to tolerate minor angular misalignments, typically within the range of 1 to 2 degrees, making them well suited for applications where shaft deflection or misalignment is likely. On the other hand, self-aligning roller bearings with their cylindrical or spherical rollers offer even greater flexibility in handling misalignment. They can withstand larger degrees of misalignment, often ranging from 2 to 3 degrees or more, due to their robust construction. This capability is particularly beneficial in applications subjected to significant shaft deflection, thermal expansion, or dynamic operating conditions. Understanding the allowable misalignment for each type of bearing is crucial for ensuring reliable and smooth operation while maintaining optimal load distribution and reducing wear and stress on components. Moving on to the next segment of our exploration, we'll systematically examine the primary types of common bearings, briefly discuss their applications, and assess their load performance capabilities. Join us as we break down each type, shedding light on their distinctive roles in the engineering world. We will start with the most common type of bearing, the deep groove ball bearing. These bearings offer low friction, smooth operation, and an extended service life. A deep groove ball bearing comprises an outer ring, a set of steel balls, a cage to retain the balls made from brass or steel, rivets to secure the cage ends, and an inner ring. The inner and outer rings feature deep, raceway-shaped grooves that enable the bearing to accommodate both radial and axial loads. Specifically, deep groove ball bearings excel at handling moderate radial, axial, and combined loads. However, a single deep groove ball bearing isn't well suited for moment loads. Given their proficiency in managing moderate loads, they're ideal for applications such as electric motors, fans and blowers, power tools, and household appliances. For each bearing type, we'll use the template shown to assess performance based on the 4 primary bearing loads discussed earlier. The rating system spans from 0 to 4 points, with 0 indicating poor performance and 4 denoting exemplary performance. Next up are cylindrical bearings. They feature cylindrical rollers for their rolling elements, allowing them to handle high radial loads. The rollers are guided by the ribs of the inner or outer rings. Without ribs, either the inner or outer ring can move axially. This makes them suitable as free side bearings, accommodating shaft expansion. With ribbed configurations, the bearing can effectively carry a minor axial load between the end of the rollers and the ribs. Moreover, they come in both single and double row designs, offering a diverse range of configurations. Now, looking at the cylindrical bearings' load performance, they excel in radial loads, earning a rating of 3 chevrons. However, their standard setup isn't optimized for axial loads. Although adjustments can enhance its axial load capacity in its unmodified form, the cylindrical bearing is not ideal for either axial or combined loads. Furthermore, its ability to handle moment load is limited unless it's paired in opposing directions. Ultimately, these bearings shine in applications demanding heavy radial load, making them top choices for drive shaft bearings, rolling mills, and mining equipment. Tapered roller bearings consist of tapered rollers, a cage, and two tapered inner and outer races. Tapered roller bearings are designed so the inner-outer ring raceway and apex of the tapered rollers intersect at one point on the bearing center line. Their tapered design enables them to support both radial and axial loads effectively. Moreover, they provide smooth and efficient load distribution, reducing the risk of edge stresses and increasing the bearing's longevity and reliability. For bearing load performance, they earn 3 points or excellent for radial load handling and 4 points or exemplary rating for axial loads. They are also highly capable of managing combined loads, thus earning an excellent rating in that category. However, single tapered roller bearings aren't designed to effectively accommodate moment loads. Tapered roller bearings can withstand thrust forces generated during cornering or heavy loads, making them popular in automotive wheel hubs and gearboxes. Moving further down our list, we arrive at spherical roller bearings. These bearings stand out due to their ability to accommodate misalignment. They feature barrel-shaped rollers arranged in 2 rows in a spherical outer ring raceway. Such a design ensures that the barrel-shaped rollers, guided by the inclined raceways of the inner ring, can adjust or realign themselves freely along the concave outer ring raceway. Examining the bearing load performance chart for spherical bearings reveals their exemplary capability in managing radial loads, for which they earn top marks. While they can handle axial loads, they don't excel in this regard, garnering 2 points. Their excellent capability in managing combined loads earns them 3 points. Owing to their distinct design, they can also manage some moment loads. As highlighted, the advantages of spherical roller bearings enable them to accommodate heavy radial loads, misalignment between shaft and housing, exceptional resistance to shock and vibration. This makes them perfect for use in the railway industry's axle boxes, construction machinery, the oil and gas sector, and wind turbines. Next, we have the needle roller bearings, which are highly valued for their compactness, making them suitable for specific locations with limited space. These bearings consist of needle-like cylindrical rollers housed within a thin outer ring. It's worth noting that these rollers are often supported by needles. Their streamlined design allows them to manage high radial loads despite their modest cross-sectional area. A review of their bearing load performance reveals their excellent abilities in managing radial loads. However, they would be ill-suited for applications subjected to significant axial and combined loads. As for moment loads, substantial moments can lead to uneven stress distribution within the bearing, potentially resulting in premature failure. Aside from their compactness, needle roller bearings are distinguished by their robust load-carrying capacity and ability to minimize friction, making them a prime choice for high-speed operations and precision machinery. Owing to these characteristics, needle roller bearings are commonly used in areas with limited radial space, such as in internal combustion engines, motorcycles, aerospace applications, and robotics. Come across a type reminiscent of the deep groove bearing, but with an added enhancement, the angular contact bearing. While they share similarities with deep groove ball bearings, such as comprising a set of steel balls, a cage, and inner and outer rings, the angular contact bearings have a distinguishing feature. As highlighted in the animation, the inner and outer ring raceways are inclined relative to the bearing axis. These features, known as the shoulder edge and the relief edge, play distinct roles. The shoulder edge provides structural support and manages axial load, while the relief edge is instrumental in reducing stress concentrations that might arise at the shoulder edge. This configuration allows them to withstand both radial and axial loads simultaneously, with the contact angle determining the load capacity. Analyzing the bearing load performance chart for these bearings showcases their capability in handling radial loads, securing 2 points, and excel in managing both axial and combined loads, earning 3 points for each. Though not inherently designed for moment loads, their distinct design enables them to bear minor momentary loads. Angular contact bearings find frequent utility in pumps and compressors, vehicle steering systems, and medical equipment. Their ability to handle combined loads and high stiffness contribute to improved equipment performance and reliability. Next, we're showcasing a distinct type of bearing with exceptional attributes, the self-aligning bearings. Designed with 2 rows of balls or rollers and a spherical outer ring raceway, these bearings possess a distinctive feature. The rolling elements in one row don't precisely align with those in the opposite row, but are centered between the 2 opposing rolling elements. This special configuration in the bearing ensures that loads are evenly distributed between both rows, maximizing the bearing's load, carrying capacity, and minimizing wear. In situations of shaft misalignment or mounting errors, traditional bearings might face challenges, risking premature wear or failure. However, the self-aligning bearings with their staggered elements smoothly handle such issues, achieving uniform load distribution and maintaining smooth operation. While these bearings are predominantly designed to address misalignments, their load performance chart indicates a highly possible application scenario for radial loads where they earn 2 points, with their axial load slightly trailing their radial load rating and earning only 1 point. In combined loads, they score similarly. When it comes to moment loads, a single self-aligning bearing is not ideally suited to handle them, but can manage minor moment loads. In conclusion, this specialized construction of rolling elements is a clever design feature that allows the bearing to accommodate and correct for misalignments, leading to increased operational efficiency, reduced wear, and extended bearing life. Their value becomes evident when we consider their frequent deployment in applications vulnerable to shaft deflection or alignment issues, such as conveyor systems, steel rolling mills, and agricultural equipment. Introducing the final type of bearing for our exploration: thrust bearings. These specialized bearings are meticulously designed to handle axial loads and consist of rolling elements, such as balls or rollers, sandwiched between 2 raceway rings. They ensure smooth and efficient axial movement, mitigating damage from excessive thrust forces and improving the overall performance and longevity of the machinery. An examination of the bearing load performance chart for thrust bearings highlights their outstanding capability in managing axial loads, earning them top marks. However, they aren't designed to handle radial loads, with the exception of thrust spherical roller bearings, which can manage minor radial loads. They also aren't equipped to handle combined loads, and, unsurprisingly, are not built to accommodate moment load. The benefits of thrust bearings include their ability to handle high axial loads and their compact design, which is invaluable in space-restricted applications. Thus, they find common use in turbochargers, vehicle clutches, aircraft engines, and HVAC systems. In our next video, we will present real-world examples of the applications for each type of bearing we discussed in this video. Meanwhile, we will talk about the load distribution for each of the bearing types and their applications. Now, let's give you a quick preview of our upcoming video on bearing applications here. Thank you all for joining us on this exploration of bearings basics and types. If you found this information valuable and enjoyed the video, please give it a thumbs up and don't forget to subscribe to our channel for more insightful content. Until we meet again, keep learning and stay curious. Goodbye.